You don't see questions like this very often on tests at school, and that's what the SAT is counting on. How many three-digit numbers have the hundreds digit equal to 4 and the units digit equal to 7? Okay, you just want to find a pattern here. And let's find our pattern. We want a 4 in the hundreds digit and a 7 in the units digit. So we have 407, 417, 427, 437, 447, 457, 467, 477, 487, and 497. We've got 10 of these numbers. Here we're told that 4 tests are to be given, and we want to know how many combinations could the test be given in. Okay, anytime you have a completely random event, you can use the factorial. And remember that a factorial is the product of all the positive integers less than or equal to n, in this case 4. You can use this for combinations when it's completely random. In this case it would be 4 factorial because we have 4 tests that we can give it in any order. And that's 4 times 3 times 2 times 1. And 4 times 3 times 2 times 1 is 24. These problems aren't that tough when you realize that you can use the factorial. Now this is a combination problem that places constraints on you. It puts limitations there. It says you've got 5 playing cards, a king, queen, jack, 10, and 9. They're set in order on a table. How many different arrangements are possible if no face card, that's a king, a queen, or a jack, is at either end? Okay, for example, it gives you 9, jack, queen, king, 10 is an acceptable arrangement. Okay, what we want to do here is work it out until you can establish a pattern. Okay, let's just say the king is going to go first. Well, we can have the 10, king, queen, jack, 9. Let's flip the ends there and say now we have a 9, king, queen, jack, 10. Now let's switch the jack and the queen, and we've got 9, king, jack, queen, 10. And let's flip the 10 and 9 again. Now we've got 10, king, jack, queen, 9. Okay, we've got 4 combinations that are possible with the king coming first of the 3 face cards. And we'd have 4 combinations for the queen coming first, and 4 combinations for the jack coming first. Therefore, we'd have 4 times 3 combinations. We've got a total of 12 possible outcomes. Now this is one where we want all the 4-digit integers greater than 5,600 that have the digits 2, 3, 5, and 6 with no repeats. So how many numbers are in this set? Okay, let's start easy. We've got 5,623 and 5,632. Well, that's as high as we can go above 5,600 with the 5 in the thousands place. Let's see what we can do with 6. Well, we can do 6,235, 6,253, and then we can repeat that with the 3, 6,325, 6,352, and 6,523, and 6,532. So we've got a total of 8 combinations. Now, the quickest way, how long did that take us to do that? It didn't take us very long to do it. The quickest way to do this problem is simply to sit down, work it out, and do it, rather than trying to figure out some kind of mathematical equation you can devise. Just work it out. Doesn't take very long. This is a problem that when you first read it, it looks a bit daunting. Here you've got a job that requires 3 painters. They have 6 experienced painters and 6 trainees. A team consists of 2 experienced and 1 trainee. How many different such teams are possible? The easiest way to do this is center on the 1. Let's say that we've got A, B, C, D, E, and F. Those are our 6 trainees. And our experienced painters are 1, 2, 3, 4, 5, and 6. Set it up, work it out till you find a pattern. A could be with 1 and 2, 1 and 3, 1 and 4, 1 and 5, and 1 and 6. A could be with 2 and 3 because he's already been with 1 and 3. Could be 2 and 3, 2 and 4, 2 and 5, and 2 and 6. A could be with 3 and 4, 3 and 5, 3 and 6. A could be with 4 and 5, 4 and 6. And A could be with 5 5 and 6. Okay, we've covered all the parameters here, and you can see that it adds up. 5 plus 4 plus 3 plus 2 plus 1. We have 15 combinations for A. Well, we'd have 15 combinations for B, for C, for D, for E, and F, just as well. They'd all be identical. So, we have 6 times 15, 90 possible outcomes for this problem. Again, start working these problems. Don't sit and look at them and try to come up with some kind of formula. How long did it take us to work that? Didn't take long at all, as long as we sat down and worked it. This is a problem that puts some constraints on us, some limitations. We've got 5 plants, and they're to be arranged so that the 2 tallest are placed on the ends, and the shortest flower to be in the middle. How many different arrangements are possible? Well, let's visualize it. In effect, get the numbers out of the words. Get the arrangement out of these words. So let's say we've got the tallest one end on the left, and we've got X. That would be one in the middle. S is the short one, then Y, and then the other tall one at the end. Now let's flip the tall ones at the end and see you can do the same thing flipping the 2 mid-sized plants. So we get a total of 4 combinations here. Okay, we want to know how many distinct sums we can get by adding any 2 different numbers shown above. Okay, now we know we can get all of the numbers that we have right there by simply adding 0 to one of them. So we can get all of those sums. We can get them a bunch of different ways, but we only count each sum once. For instance, negative 5 plus 0 is negative 5. We can also get negative 4, negative 2, 2 and 4 in between them. Because, for instance, negative 5 plus 1 is negative 4. So you see we can get negative 4, negative 2, 2 and 4 as well. Now we put our attention at the ends. How many numbers can I get less than negative 5? Well, negative 5 plus negative 1 is negative 6. And negative 5 plus negative 2 is negative 7. So you see we can get negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1. 8 values. We'd also have 1 through 8, so that would give us 16 values, plus let's not forget 0. Gives us 17. Okay, here we're given a sequence, and we're given the first 4 terms of the sequence, and it says that after the second term, each term can be attained by dividing from the previous term the term before that. For example, the third term can be attained by dividing the second term by the first term. Okay, you can see that we're doing this. We divide 2 by 1, we get 2. Divide 2 by 2, we get 1. Divide 1 by 2, we get 1/2. Keep on carrying this out. We divide 1/2 by 1, we get 1/2. We divide 1/2 by 1/2, and we get 1. We divide 1 by 1/2, and we get 2. Okay, we can see that now we've gone back around with our sequence. And now we can identify our sequence of 1, 2, 2, 1, 1/2, 1/2. And then it starts repeating and recycling again. So we have a sequence of 6 numbers, and they add up to 1 plus 2 plus 2 plus 1 plus 1/2 plus 1/2 adds up to 7. Okay, how many 6's are there in 42? Well, 6 goes into 42 7 times, and there's a value of 7 for each of those 7 numbers. So 7 times 7, the sum of the first 42 terms of the sequence will be 49. That's how you do these problems. You find the recurring pattern. I don't care what sequence they throw at you, it does start repeating on the SAT. Just find that point where it starts repeating and apply it to the rest of the terms.